Hello everyone, welcome to our paper titled Resource Efficient Mountainous Skyline Extraction Using Shallow Learning. This is a joint work with Ibrahim Martin and George Bebes. I am Tokir Ahmed and I shall be presenting this paper for IJCNN. So let's go through the outline of the paper. So I shall be first discussing the distinction between sky segmentation and the problem of skyline detection. Then we shall look at some applications of skyline detection and the contribution of our paper. Then I will talk a little bit about the background and some of the formulations for skyline detection problem. Next, I am going to talk about shallow learning and how that framework behaves and how we have adopted it for the proposal of a skyline detection approach. Subsequently, I will talk about the experiments and conclude with some results. So skyline detection essentially is the problem of finding the visible boundary in an image, for example, over here, that divides an image into two main regions. One is sky and the other is non-sky. So over here in the right, we can see an image where the skyline boundary has been marked and it is dividing the image into two regions. The non-sky part of the image could be anything. It could be water, it could be buildings, it could be plains or mountains. Our focus is mostly on skyline detection for mountainous images. So one of the assumptions that skyline detection approaches make is that the path extends from the leftmost column of an image to the rightmost column, and and it is somewhat different from another popular problem, which is sky segmentation, where any general network, which is like for semantic segmentation or scene parsing, can be applied. So over there, the assumption is not that a path needs to be extended from left to right, or the boundary need to be visible, or the sky should be in just one region. There are multiple regions of the sky. So these are two related but two distinct problems, and one solution can be converted to the other solution and vice versa. Okay, so skyline detection finds many applications in modern era. For example, one of them is visual geolocalization. So visual geolocalization is the problem that given an image, you want to know the position and orientation of the camera that took this picture. So you can start from some crude estimates from the GPS, and you want to define them with given your data. So visual geolocalization is very prominent in urban setting as well, where there are so many man-made structures, and you can run your feature matching approaches over there, and you can match one image with the other and identify where the image was taken, where the query image was taken. For example, over here we are looking at like street view and the aerial view, and then you can find features around the corners of these buildings. So in case of natural environment, so you don't have anymore the structural presence or man-made architecture, and the texture of the image is going to be different. For example, I am showing here two different images taken in two different seasonal conditions. So these are going to be different into time-wise, they are going to be different. So there is nothing to match architecturally, but naturally skyline over there has a profile which lends you a cue that you can leverage to localize your images. So other applications of skyline detection are like planetary rover localization, stability and navigation of UAVs and micro aerial vehicles, as well as using skyline for example for tourism activities. For example, this is a nice app which essentially in augmented reality tells you which peaks you are pointing your camera to, and what are the names and what are their different characteristics. And skyline detection can also be used for ship detection and port security as well. So the contribution of this paper. So earlier approaches towards skyline detection, they are mostly assumed that skyline is a linear boundary, which could be the case in some situations, and it could be helpful to just detect that linear boundary using half transform, specifically, for example, UAV navigation in a planar non-mountainous area, or ship security or ship detection or port security in case of shorelines. However, for mountainous imagery, the skyline is mostly like non-linear, and it is challenging to detect because there could be a lot of natural factors involved. For example, there could be clouds, fog, or mist, as well as there could be regions which are occluded because of these. So in earlier approaches, there have been human involvement. So the algorithm relies on human to correct at least partial part of the skyline. So another issue with earlier skyline detection methods is that they are mostly very costly. They are both memory and compute hungry. So, and based on that, they are not very suitable for applications which have relatively smaller payloads. For example, mobile devices, for example, rovers, for example, UAVs, where the battery, the memory, and the compute is not like a desktop PC or something. So towards this end, we are proposing a new skyline detection approach using shallow learning, which has smaller memory footprint and very quick inference time, and the performance is comparable to those methods which are very resource costly. So over here, I am going to talk about a little bit about the skyline detection and how it is formulated in the literature as a graph search problem. So given an image, we are going to run an edge detector on it, which is going to give us this EI of G. And using that edge map, we are going to initialize a multi-stage graph G with vertices and edges and vertex cost and the link costs. So whether a pixel is an edge or not is going to be helpful here. And based on that, we are going to initialize our vertex cost with a constant. And then the link costs over here are initialized based on the connectivity of a pixel with its neighbors. Once these vertices and link costs are set, we can solve a shortest path problem using dynamic programming on this multi-stage graph, and the resultant shortest path is essentially the skyline, the detected skyline. So this is how, so there are some more steps, and I invite interested listeners to please have a look in these two relevant papers. So over here, for example, these is the black nodes are essentially the detection, the output of the edge detection. And then over here, we have like a search window where we are going to connect this edge over here with this black edge and essentially fill these gaps, because edge detection is never going to be perfect. And then after filling these gaps, we can apply our dynamic programming and essentially find a path, shortest path from node S to node T, the start and target. And this path essentially is the path that corresponds to the skyline. So people have investigated many different options for skyline continuity. So for example, based on edges, people have also explored gradient, where the gradient magnitude and the difference of the gradient magnitude and their weighted average is used to initialize the nodal costs. Similarly, in earlier work, we have explored classification. For example, sport vector machine trained on shift and hog features. And towards this end, what we have done is we have used this trained classifier in two ways. One is to essentially first identify the edges which belong to the skyline and the edges which don't. So that kind of refines your edge map. In addition to that, we have also explored the maximally stable extremal edges idea, which is to say that you only retain edges which are very stable for various thresholds of, for example, Kenny. So based on that, we define our edge map, and then using either a constant value over here to initialize the nodal cost, or the actual classification scores from the said classifier. And these classification scores are first normalized between 0 to 1 to make them tractable. So this is another approach where we don't rely on edges at all. Rather, we use classification to generate the trained classifier to generate a classification score for each and every pixel. So this kind of approach results in a dense multi-stage graph instead of a sparse graph. And of course, you can make it sparse afterwards. That is how it is shown over here. And so essentially every white pixel has an infinite score associated with it. And then you can run your dynamic programming to get the shortest path boundary, which is the skyline. So the current approach that we are proposing in this framework, it is based on shallow learning. That is a framework that has been introduced previously, and it is called as BLADE. It is essentially a generalization of a very popular super resolution approach called RAZOR. And BLADE has also been demonstrated in recent work to perform well and generalize to other computational photography applications, for example, image denoising, demosaicing, and stylization. In this paper, we have adopted BLADE for our problem of mountainous skyline detection. So essentially what we do is we have FIR filter bank, and at the inference time, based on the vicinity of the local neighborhood or vicinity of the pixel or its local neighborhood, we are going to choose a filter over here, which is H. And the selection criteria that we are using, S of I, that is based on the structure tensor, which is the local information of the pixel. So essentially we extract a patch around a pixel. So our I of Z is essentially giving us a patch around a pixel, and then we flatten it into a vector, and we choose the filter based on the structure tensor, and we apply the dot product of these two vectors and essentially get the output or output value of that specific pixel. So over here, this is how it operates. So we have, so from 1 to K, we have different FIR filters, and based on the local patch of the image, we are going to select one of these guys, and then that filter is going to be applied on this patch, and that gives us the output for this input pixel. So this was about the inference. So let's talk about how we are going to learn these filters. So what we are going to do is we are given a bunch of training images. So I am going to take the example of computational photography, where we have noisy images and noise-free images. So noise-free is our target images and noisy is our input images. So what we are going to do is essentially solve this multivariate regression over here. So we take this L2 loss along with the regularization, which is Q, which encourages filters to be smooth. And essentially this boils down to solving this multivariate linear regression for each of these H filters. So over here, how we are going to accumulate the data. So we have our noisy image over here, Z, and sorry, over here Z is our output image and U is our noisy image. So essentially we are going to accumulate these into the gram matrix G, and from given the gram matrix we are essentially can access each of these matrices A transpose A and A transpose B from these accumulated gram matrices, and these gram matrices are going to be like independent for each different filter in the filter bank. So coming back to the selection criteria, how we are going to decide how we are going to select a filter for a given pixel. So that is essentially going to be boil down to the structure tensor of the pixel and structure tensor of its local neighborhood. So essentially what we do is we apply, we get the gradient information in the local neighborhood, and this is the gradient over here is spatially weighted, and of course we can just use the Luma channel, but it has been also demonstrated that using all three color channels for getting the structure tensor is beneficial. So we are going to essentially get the weighted gradient for each of the color channels, and this is going to formulate our 2x2 matrix Ti for each pixel I, and then we are going to run our Eigen analysis or PCA based on this 2x2 Ti matrix. So once we have generated our 2x2 matrix for each of the pixel I using the local gradient information, we essentially run the Eigen analysis on that, and that provides us three different features for the structure tensor. And these are called the orientation, strength, coherence. Orientation is essentially reflects the gradient orientation. Strength is the magnitude of the gradient, and then coherence is essentially a metric of the anisotropy of the local structure. So these orientation, strength, and coherence are going to be continuous variables, and then we are going to quantize them into predetermined bins. So now putting everything together for skyline detection approach based on shallow learning. So what we do is in comparison with the computational approaches where each pixel is used, we are going to concentrate only on the pixels which are essentially the output of edge detection. So essentially every pixel which has been detected as an edge over here using any edge detector, that is where we are going to conduct our learning. And similarly during inference, we are going to first run it through the edge detection, and then the pixels which have been detected as edges, that is where we are going to apply our inference. So essentially the RK gives us a patch around pixel I comma j. So I comma j and k essentially is the same, is two different formats for the same pixel here. And then we select based on the local neighborhood of the or the structure tensor of the pixel. We select a filter and we apply it, and that cost is going to be used as our nodal cost, and then we are going to apply the same link costs over there that we have talked about, and then we solve this graph through the dynamic programming. So we can directly use these costs, but we have seen in our experiments that using the gradient strength, which is already there in terms of one of the features of the structure tensor, is helpful. So we are going to do a weighted average of these two. So over here we are looking at the pipeline of the shallow skyline detection. So essentially we are given an query image. We apply our edge detection based on this, and then only for the edge pixels, the trained filters are chosen based on the gradient or the structure tensor, and those filters are applied essentially to the given image. And these are over here. We are looking at the prediction scores for the different pixels, and we can see that the red intensity reflects the most likelihood of a pixel belonging to the skyline. So after we have a prediction map like this, we can combine it with the gradient strength, which is a part of a structure tensor, and that gives us this image in pan E. And essentially the pan E is the nodal cost, so essentially a dense graph, multi-stage graph, which is then solved through dynamic programming to give us the resultant boundary, which is the skyline. So we have evaluated our proposed approach on 4 different data sets, which are very conventional in the skyline detection literature. One is basalt hills, which is relatively a smaller and easy data set. Web dataset, which is comprised of 80 images. It has some seasonal and viewpoint variation, but I would say it is a moderate dataset. CH1, it is a prominent dataset and it has more than 200 images. And it is somewhat challenging because the original authors have reported human involvement for at least 50% of the images. And the most challenging dataset that we have explored is GeoPose 3K, which is essentially a dataset for visual geolocalization. And as I said, it is one of the most hardest datasets that we have. So we are using two different metrics for comparison. One is average absolute pixel error, essentially how we take the distance between the detected skyline and the ground truth skyline and essentially average the vertical distance. And the other is essentially just average of the correctly classified pixels, so just the average accuracy. So over here we have used CH1 dataset as the training set, and we have used basalt hills and web data as the test set. And over here we are looking at the mean absolute average error. Next, we have looked at the size variation for the filters. So we have ranged from 7 by 7 up to 15 by 15, and there is not essentially very much gain or loss based on the window size or the filter size, but the 7 by 7 filter is going to be the faster one. Then we have looked at the ablation for the variation of the data. So essentially used one of the datasets as training and used the other two as the test set. And we can see that in case of CH1 the dataset, which has more versatility, the output of the basalt hills and web is prominent compared to when one of them is employed as the training data. Over here, there are some results. So each skyline detected boundary is marked in red color. So there are some examples with good detection for our method. And then there are some failure examples. For example, it is confusing part of another mountain terrain as part of the skyline. Similarly, over here, the road, since it is kind of a linear line, it is taking that, and it might be less costly instead of taking the non-linear skyline over here for it. Over here, it is missing the part of the skyline as well and taking another mountain. So we have compared our approach with the existing benchmarks on the GeoPose 3K dataset and using the metrics that they have previously used. And this is our standing, which is very close, I would say, to the other methods like these Horizon DCS SI. And next we will look at, so this dataset, GeoPose 3K dataset, is quite challenging, as I said earlier, and it has many images where the skyline is not even visible. So for example, we can see these several examples from GeoPose 3K, where a human even cannot mark the boundary of the skyline without domain knowledge or without relying on other cues, for example, digital elevation models, or for example, Google Earth or Google Maps. So our paper was focused on proposing a resource efficient skyline detection method. And over here, we are comparing the memory footprint and the inference time. So conventionally, deep learning methods are mostly applied for skyline detection, or there are other methods based on supervised learning, which are relatively inference-wise very costly. So our approach, proposed approach with a 7x7 filter, essentially gives you a better better trade-off between the memory and the inference time versus the performance. And it is to be noted that a lot of these can be further parallelized, and this is just like you can say the crude estimate of the time where the implementation is not very efficient. So to conclude, we have looked at skyline detection at its application. We have identified the differences between the two related but distinct problems of skyline detection and sky segmentation. And as I mentioned earlier, skyline detection is quite challenging, especially the non-linear version of it. And mostly the existing solutions are very costly. So towards this end, we have proposed a skyline detection approach using shallow learning, which demonstrates comparative performance while providing a good memory and computational footprint. And so the proposed skyline detection is, I think, very suitable for resource constrained platforms, for example, UAVs, rovers, or mobile devices. And we have also identified some of the challenging issues with the existing benchmarks, like in GeoPost 3K. And so these different dimensions, for example, exploring how we can use skyline detection for such challenging approaches, such challenging data sets, that is going to be the next avenue of the research. So thank you very much for listening. And if you have any questions, please feel free to contact me. I have provided the contact information for all the authors, and our code is also available. So please feel free to look at it. And thank you very much for your time. And let me conclude.